Okay. Okay, it's working now. Okay, so when will you say, if you're using this number, I know it's going to be exact? What number? And what concept is this?
Is the infinity?
Exactly. What concept is this when we talk about something like this? What concept? From everything we studied so far in this class. Where did we? Thank you. Indeed. So the limit as n approaches infinity, from what? From the sum of areas. All areas. Sum of all areas. This will be the exact area. Absolutely. The moment I am able to find the limit as the number of subintervals goes to infinity from the sum of all rectangles, that will be guaranteed to be the exact area. Before I finish this up, I have to talk about a notation called the summation notation. And I'll come back. So our next topic, before we go back and finish that up, is the summation notation, also called sigma notation. What is this all about? Okay. Let's suppose I want to add 1 squared to 2 squared to 3 squared to ... let's say 10 squared. There is a way of writing this condensed, in a condensed form. So I see that the first element in the summation is 1. The last element is 10. The notation for the sum is this. It's basically S, but it's the Greek letter S, which is called sigma, uppercase sigma. We also have this. This is also called sigma, but this is the sigma notation. It's the S, the Greek letter S, and it starts with I, which is the index, from 1 till the last, which is 10. Of what? Of I squared. Okay, let's go back and explain this. When I is 1, I have 1 squared. Done. Sum plus. When I moves on to 2, this is the lower limit. This has nothing to do with this word of limit here. So lower limit, 10 is the upper limit of the index. Has nothing to do with the word lim that we've been using with the operator lim. So when I is 1, I have 1 squared. The sum says plus. When I is 2, I move on to the next index, 2. I get 2 squared plus. This when I is 3 and ... when I is 10. This is the condensed way of writing such a sum. Now I could have something like, for example, let's say 1 cubed plus 2 cubed plus ... Let's say plus n cubed. Well, that is going to be I. You can use I, J, or K. Let's use J this time for index. From 1 to n. It starts with 1 and goes sequentially till n, from J being 1. So this will be from J to the 3rd. I could have a summation notation of the sum of 2 terms. Like, for example, I squared plus 3I cubed. Let's say from I equals 1 through 4. What will this represent? Okay, when I is 1, I have 1 squared plus 3 times 1 cubed. Plus, when I is 2, I have 2 squared plus 3 times 2 cubed. Plus, when I is 3, I have 3 squared plus 3 times 3 to the third. And plus 4 squared plus 3 times 4 cubed. And I determine that sum. That's what this represents. There are two properties that I need to mention about the summation notation, and then I can go back and finish up what we started. So two properties. Of the sigma notation. And here they are. The sum of a generic term, let's say AI plus BI, when I goes, let's say, from I to N, or I could have a difference, is exactly what you would have expect, the summation of AI plus the summation of BI. These are generic terms, So from I equals 1 through N, from I equals 1 through N. So if I have a sum of two general terms or two terms, I can separate and write the sum of the summations. If I have a difference, I can separate. I'm not distributing this symbol, although that's what it looks like I am. No, so it's the sum. The sum of the difference of two generic terms can be presented as the difference of the two sums. So this is property 1. It's two properties, but I like to connect them. And here's the second one. If we have the sum from a constant times AI, from I equals 1 through N, of course, the constant will go in front. We are going to use both properties in everything we're going to look at in chapter 5. Okay. One last thing before we attempt, we go back. So I don't like saying this to you. I'm more than willing to prove any of this. So identities. There are 4 identities that you have to have in your notes or remember them. The sum of 1 from I equals 1 to N is N. You're adding 1 N times. The sum of I from I equals 1 through N, this is N plus 1 divided by 2. I'm going to jump to the fourth one because these two are connected. Easy to remember. I to the third from I equals 1 through N is the same but squared. And the last one, of course, is the sum of I squared. I equals 1 through N, which is N plus 1, 2N plus 1 over 6. I'm more than willing to show if you want to prove any of this using mathematical induction.
Can you move the paper down a little bit?
This way?
The other way. I do have a question about the first identity. Since I isn't in the equation and it's just 1, why would
Excellent.
it be equal to N?
Excellent. Excellent question. Let me show. So if I have the sum from I equals 1 through 10 of 1, when I is 1, 1. Summation says plus. When I is 2, plus 1, plus. When I is 2, plus 1, plus. When I is 3, plus 1, plus. When I is 10, plus 1.
Gotcha. So even though I isn't in the equation, we're still adding 1 every single time.
Yep.
Gotcha. Thank you.
Yep. Thank you. Okay. Any questions on this? Now I'm going back to page 9. How do
Actually, yeah, can we go over the third identity really quickly too? I would like to know where you got the 6 from.
Oh, that's what I said. If you want me to prove any of these identities, I have to use mathematical induction to prove them.
Okay, gotcha.
Yeah, these are these identities. We have to memorize them normally in class. When we take tests in class, in person, my students have to memorize these 4. Now we're not taking tests in class, so if you want me to prove any of this, let me just show you an application of this, how useful they are. Let's say for whatever reason you want to add the I equals 1 through which number? Give me any number you want.
14.
14 of I. Okay? So this is, by definition, it's an identity. It's n plus 1 over 2. 14 times 14 plus 1, which is 15, divided by 2. So this is your answer, 7 times 15. 105. If you want to determine the sum of any of this, put any n you want. Just plug it in, and you get the answer right away. These are identities. Yes?
I was just wondering, when would you be able to show us proofs for some of these?
Oh, if you want to use mathematical induction, I can show any of those. You can choose one, and I can show you mathematical induction. You don't have to prove them in this class.
For the third one. Yeah, I get that. It just helps me understand it better. If I
yes, of course. Of course. So you want to prove the third one?
Please.
Oh, yeah, sure. So mathematical induction it's not done in this course. It's in a previous course, either pre-calculus or college algebra, depending on where you take either one. Okay, so mathematical induction has 2 steps. In step 1, so I'm just going to copy because we chose to show this. The I squared equals n plus 1 to n plus 1 divided by 6 from I equals 1 through n. Okay, so I can move this away. Okay, so basically, I'm not going to use this notation in order to explain how we prove this. So I'm going to use 1 squared plus 2 squared plus dot, 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 plus n squared equals n plus 1 to n plus 1 divided by 6. Okay. In step 1, we pick, let's say n equals 1. For n equals 1, I have 1 squared. That's it. That's one element when n equals 1. And now I plug in here, and I have to get 1. I plug in 1. 1 times 2 times 3 divided by 6. Yes, it is 1. We do not have to pick more than one element. We normally pick n equals 1, but it doesn't matter. You can pick anything you want. But if you pick 2, you have this plus this. And then you plug in 2, and they have to equal each other. If you pick n equals 3, then you have 1 squared plus 2 squared plus 3 squared equals replacing n by 3. That's why we only do it for the first. Here's the second step. Step 2 is the what is called induction step. And here's how we proceed for the induction step. Assume we're going to denote this statement. This is a colon. Pn. Assume Pn is true. Show Pn plus first is true. If Pn plus first is not true, then my assumption was wrong. And I will say, sorry, P sub Pn, or written like this with parentheses. It can be done the same. It can be denoted like that too. Show that Pn plus first is true. If I show that this is true, obviously the assumption I started with is correct. So what does Pn plus first mean? Okay, Pn plus first is a statement with n plus another term. So from here, I will have Pn plus first is 1 squared plus 2 squared plus dot 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 plus n squared plus n plus first squared. And now, as I mentioned, I have to replace n by n plus 1. N plus 1, n plus 1 plus 1 will be n plus 2, and 2n plus 2, n plus 1. I had to replace n by n plus 1. I distributed, and I got 2n plus 2, n plus 1 divided by 6. At this step, I will say, well, wait a minute. Because I assumed that Pn, the statement Pn is correct, then it means that I can replace all this, because I assumed it to be true. I can replace it with this. They are the same. All this can be replaced by n plus 1 to n plus 1 divided by 6. Okay, all I have to do now, and this is it, all I have to show now is that when I replace this in here and I add n plus 1 squared, I get this. If I don't, then I'll go back and say, oops, sorry, my assumption is wrong. If I do get the same thing, I will say, by mathematical induction, the left-hand side equals the right-hand side. And moving forward, we have to remember that y squared plus 2 squared plus dot 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 plus n squared equals this. Good. So all I have to do is add n plus 1 to n plus 1 divided by 6, and plus n plus 1 squared, and see what I get. I better get this, which, let me simplify it a little bit. N plus 1, n to n plus 3, and then n plus 2. Okay, we'll get back to that. Of course, I'm not going to distribute all this. I see that these two terms have n plus 1 in common. Of course, I'm going to factor it out. And I will distribute now 2n squared plus n divided by 6. And this is plus n plus 1 because I took one of them out. I will multiply both by 6. I get n plus 1, 6. 2n squared plus n plus 6n and plus 6. And this is n plus 1. And this is 2n squared plus 7n plus 6 divided by 6. I don't know the factor form of this. But if it's not 2n plus 3 and n plus 2, then I'm in big trouble. And I will check right now. 2n times n, 2n squared. 2n times 4 plus 3, 7n. 3 times 2, 6. This is it. So our assumption was correct. I used the statement to create the next statement, and it worked. So then my assumption is true. Meaning 1 squared plus 2 squared plus dot 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 plus whatever you want to stop at squared is this, with the stopping point, with the stopping value. And that was the mathematical induction. It has 2 steps. One step is when we